Alright, so after all that work on all those exponent laws, we're going to move ahead and investigate exponential functions. So you haven't dealt much with these at all over your previous years or units. So there's a lot going on here that's worth looking at. And I will say, before you get too far in this unit, you should have already done the investigation using Desmos, investigating exponential functions. The sheet looks something like this. So again, if you haven't done so yet, do that first. Okay, you're going to want to read through what's there and graph everything that's there and see if you can figure out some of the different features of the graph. Okay, but if you've done that already and you have some questions, this will be a good chance to get some of those questions answered first. Okay, so the first thing I want to look at is just look at the basic function, some base we're going to call a all to the power x. Okay, and right now I have it set up so that the base of this function, the a, is going to be equal to 2. Now, in terms of our parent function, you're used to, when you're dealing with quadratics, that the parent function, the base function, is y equals x squared. With sin x and cos x, it was just sin x or cos x. The base can be absolutely anything for a parent function. So if you see what happens here, I can change the base, make it a little bit higher. You can see change the graph a little bit. But 3.5 to the exponent x is its own parent function. 2 to the exponent x is its own parent function. So whatever that base is its own parent function. You can see what happens here. So as I change the base, you'll see it change the shape of the graph. But you'll see what happens as I bring the a all of a sudden below 1. You'll see the general shape of the graph changes. I go from having a graph that's going up from left to right to a graph that is going down from left to right. So that's the distinction between a graph that is increasing versus decreasing. So one of the things it asks you on that worksheet for everything that you're going to graph is this function increasing or decreasing? So whenever we say a function is increasing, it is getting larger from left to right. So think of it as you're climbing a hill. If we say a function is decreasing, like this one right here, means you're going down from left to right. Okay, the next thing worth mentioning, one of the first things it mentions on this investigation is the idea of a horizontal asymptote. And it's defined as a horizontal line in which the value of a function approaches as the value of x approaches either infinity or negative infinity, i.e. as it moves out to the left or out to the right. So visually what that looks like on a graph, let's just say we take this graph, which is y equals 0.7 to the x. What you're going to see is as x moves out far, far right, it appears to be approaching a specific value. In this case, it appears to be approaching the x-axis. So the equation of a horizontal line there, if you picture that being y equals 0, you'll see if I zoom in on the graph here that the function gets closer and closer and closer to y equals 0, but no matter what, it's never actually going to touch it. No, I can always zoom into a certain point and see there's going to be space in between the function and 0. As I move out further to the right, it does get closer and closer. So in this particular case, y equals 0 is considered an asymptote. Okay, so again, it's an invisible line that the graph gets infinitely close to but never actually touches. Okay, and you can see, let's say I make this y equals 1.8 to the x as an increasing function. Again, the asymptote's still at y equals 0. As it moves out far and far out to the left, you'll see that, again, eventually there's going to be space between that function and the line y equals 0. Okay, so again, we get infinitely close to the y-axis without actually, to the x-axis without actually touching it, so y equals 0 is the asymptote. Okay, and again, you can create exponential functions of asymptotes just about anywhere. So as I zoom out right here, let's say I create the equation g of x equals 3 to the exponent x minus 2. Okay. Again, I still have an asymptote here. Any exponential function will have an asymptote. This particular one is going to have an asymptote at y equals negative 2. Okay, and so again, I'll get infinitely close to that line without actually touching it. Okay, so we'll talk about how to find the asymptote coming up a little bit, but that's what an asymptote is on a graph. Okay, so with that in mind, there's a lot more else to talk about, right? There's still lots to do with transformations and how each of the transformations affects different features of the graph. You'll see on this worksheet you're asked not only was increasing or decreasing to find the horizontal asymptote, looking at domain range and how to find the x and y intercepts, or whether or not there is an x-intercept and how to find the y-intercept, and looking at mapping. So we're going to look at all of that. But before we get into that, I just want you just to quickly go over the definition of increasing, decreasing, or neither, and see if we can get those definitions down pat. So I asked you to look at these 5 equations. You can quickly plot them into Desmos, or maybe if you can get an idea from the equation of what's happening, just try and predict whether the function is going to be increasing or decreasing from left to right, or if it's neither increasing or decreasing, if it stays flat. Okay, so give those a quick try on your own, and see what you can predict without necessarily making a graph, and push play and ready to go through them together. Okay, so let's take a look at these graphs here. Now, a couple of these we should be able to predict without actually having to necessarily make the graph. So, for example, looking at the middle two, the second and third one right here, y equals 3x plus 7, we know what that looks like from grade 9, right? This is the equation of a line, and if you'll notice here, the slope is 3, and the y-intercept is 7. So if the slope is 3, that means that it's moving up 3 for every one we move to the right. So this is actually increasing from left to right. We should be able to tell that just by looking at the equation. If we make a graph, we can see, again, it's increasing from left to right. As for the third one, again, it doesn't necessarily look like a form that you're used to seeing. Remember, this is point-slope form of a line. What this is telling us is that the slope of this line is negative 5, and that it passes through the point 6, negative 2. So again, 6, negative 2 is right around there. There we go. And you'll see that, again, since the slope is negative 5, it is decreasing from left to right. So those two we should be able to get just by looking at the equations. Okay. Now, as for a couple of other ones we should be able to get just based on what we looked at very quickly looking at parent functions of exponential functions. So y equals 2 to the x. You'll see there's no transformations done to this one. It's just a plain number all to the exponent of x. So this one, as we saw, if the base is larger than 1, we are increasing from left to right. And you can see, look on a graph, that is actually happening here. So we're increasing from left to right. Over here in y equals 0.5 to the x, our base is less than 1. This one should be decreasing from left to right. And again, we see that it is decreasing from left to right. Okay. Now, if you look at the middle one here, negative 8 times 2 to the x, this one actually is a little bit different. Again, we have the 2 to the x here, which might make us think it's increasing from left to right. What's actually happened here, this negative 8 out in front, if you can picture what something outside the function multiplied does, just like it did with quadratics or with a sine function, this causes not only a vertical stretch by factor 8, but a reflection across the x-axis. So you picture what this one looks like in terms of a shape. Picture what the shape would look like if this was reflected across the x-axis. All of a sudden we have something that might be decreasing from left to right. Let's see what this looks like. And then all of a sudden you can see, hey, we are actually now decreasing from left to right because of that reflection that's happened there. Okay, so again, looking at those graphs there, we can see plainly whether it's increasing or decreasing from left to right. Okay, and now let's see if we can find out a whole bunch of other information just by looking at equations. So what I am going to do first, though, is actually take a look at generally what's happening. Function moving left to right, vertical stretch, vertical compression, reflections. See what happens when we do that with parent functions. Okay, so what I've graphed here is just a run-in-the-mill function. Right now it's just 2 to the x because I haven't changed a vertical stretch or reflection. I haven't changed a vertical shift. I haven't changed a horizontal shift. But I've chosen the base here to be 2. And again, in terms of a parent function, this base could be absolutely anything with the only restriction that it can't be negative. It doesn't make sense to have a negative base in this particular situation. And I'll leave it to you to think about why that wouldn't be the case. So here, right now this is 2 to the x, and I just want you to see what happens as we change a. So as we change a, okay, it is going to get a little bit steeper, as you can see. But the big thing what you see is as a gets negative, all of a sudden you have a reflection. Okay, so this will change this. If you want to think of it as opening up or as opening down, I suppose you can. It's not technically a parabola, so it doesn't really open up or down. But the best thing to think about is that it's actually going from increasing to decreasing. The base function on its own, the 2 to the x, is increasing, but the moment we make that a value negative and add that reflection, it's now been reflected, and now it's going from decreasing. Let's say we're to change this base something less than 1, like let's say I make it 0.8. Okay, now if you just look at the parent function, it's now decreasing to start, but once I change that a value being negative, you have that reflection, and now it's gone to increasing. So having that reflection now changes the graph from increasing to decreasing, or vice versa. Okay, the other thing I'd like you to see, let's see how as I change h, as you'd expect it, just like with quadratics or sinusoidal functions, it's just a horizontal shift left to right. Okay, and if you want to look at k, you can picture k being a vertical shift up or down, depending on that value of k. The other nice thing worth noticing here, if you're looking for the asymptote, it actually does follow that vertical shift, which kind of makes sense, right? On the parent function, the asymptote's at y equals 0. Okay, let's just make this parent function again. Okay, the asymptote's at y equals 0, so it's going to shift up and down according to that vertical shift. Okay, so you can very quickly see your equation of your horizontal asymptote by seeing that k value. It's going to be y equals whatever that k value is. Okay, so with that in mind, let's go and take a look at y equals 2 to the x plus 5. Okay, so we can click and make a sketch on this one on Desmos just so we have an idea. Okay, so a lot of this you can answer from the graph, but let's see how much we can answer just by looking at the equation. Okay, so in terms of our parent function, you're always going to get our parent function just by looking at the main power right here, so without any transformations. So in this case, the base was 2, so our parent function is just going to be y equals 2 to the x. Okay, now for our mapping rule, think about what's happening to x. What's happening to the exponent? The exponent hasn't changed one bit, so the mapping rule is still going to be x. Okay, as for what's happening to y, well, there is no reflection or vertical stretch or compression there, so there's nothing multiplied by y. We do shift everything up 5, so our mapping rule is simply going to be x, because nothing's changing for x, and then y plus 5. Okay, our horizontal asymptote, you can see it on the graph here, it's going to be at y equals 5. Okay, that's the line we get infinitely close to but never actually touch. Okay, the easiest way to see it though is just take a look at that vertical shift in the equation. Okay, so the horizontal asymptote is going to be y equals 5. Okay, as for your domain, if you look at this graph here, x continues on forever in all directions. Okay, it does get steeper and steeper, but it does continue on forever to the right, continues on forever to the left as well. So the domain here is simply going to be x an element of all real numbers. Okay, and as for our range, we have to be a little bit careful here, because looking at the range, you see that there's no y values that exist below the asymptote. Okay, and specifically, there's no y values that exist at the asymptote either, because we get infinitely close to the asymptote but don't actually touch it. So the only y values that are possible are ones that are strictly greater than or strictly above the y value of that asymptote. So our range here is going to be y is anything larger than 5, and it has to be strictly larger than. If you write larger than or equal to, it's wrong, because then you're saying it's equal to the value of the asymptote, and it's not. Okay, so the range is strictly y is greater than 5. Okay, you can picture this when it had been reflected. Then let's say this was reflected right here. You could see that the range should be anything less than 5, because again, now you have all y values existing below the asymptote, not above. Okay, the next thing to look at here is whether or not this graph has an x-intercept, yes or no. So again, we can look at the graph for that. You'll see that this particular graph never crosses the x-axis. Okay, so if we can see never crosses the x-axis, then we can simply say there is no x-intercept. Okay, as for the y-intercept, let's take a look at it on the graph. We can see it's at 6. Okay, now how would you calculate that? Well, remember, you can always calculate the y-intercept because it always occurs when x is equal to 0. Okay, so we can always take our equation here, which in this case was y equals 2 to the x plus 5, and sub in x equals 0. So just to show you how that would work, we'd have y equals 2 to the exponent 0 plus 5. And you know from your exponent laws from earlier on in this chapter that 2 to the exponent 0 is 1. So you get 1 plus 5, which is where you get the y equals 6 for your y-intercept. Okay, and last but not least, is it increasing or decreasing? Well, you can see very easily from the graph that it is in fact increasing from left to right. So we can say this one is increasing. Okay, we're going to look at later how to create a sketch, putting everything together from the equation to make a quick little sketch so you can see a lot of this without actually having to have Desmos. You can be able to do it by hand. What I'd like you to do first, though, is try and complete this chart. Here's another equation. Y equals negative 3 times 0.7 the exponent of x plus 2. So try running this through Desmos, see what you can get, and we'll run through the solutions together in part 2 of the videos. So we'll see you over there.